Okay, so let's finish this question from the end of the last video. 4 squared is 16, negative 16 on the top, negative 4 on the bottom. Delta D2 is going to equal 4 meters. So the total distance, which is D1 plus D2, 4 plus 2 is 6 meters. 6 meters is less than the 6.2 meters, so he will not hit the teacher. Okay? So that's done. So hopefully these are getting somewhere close to easy for you. Yesterday I had said that if we were actually in class, at this point I would give you this sheet, one last sheet of kinematics problems on it. It's the last this time. And I would ask you to do it as an assignment. The first ones are 1 part, okay? Doesn't get to 2 parts until number 6. So you should be able to do the first ones like 2 minutes and less. And then as they go down and get into 2 parts, it would take you a bit longer to do these ones. And then of course there's 3 more in the back. And so I would say sit at your kitchen table or at your desk in your bedroom with loose leaf and time yourself. Because really now the easy ones should be getting quick. And of course I would say time yourself because I'd be thinking of a classroom test where you'd have a limited amount of time to do it, and that you should be able to move through the easy ones pretty quickly, leaving you more time with the 2-part ones. Okay, so I would still suggest you work on this and see how you can do. Okay, but really, with the exception of that and one more question that I'll wait until another set of videos to give you, that is the end of kinematics. But it is vitally important, kinematics is, so you need to make sure you can do these and that you just don't watch me do them. Okay? After kinematics, we go to forces. So we are finally about to start unit number 2. And unit number 2 is with forces. And it has 2 parts to it. Statics, forces do, statics, and dynamics. And if you were to look back in your notes from the beginning of this course, you would remember that I told you that we were starting with something called mechanics. And any good physics course starts with mechanics, and it has 3 subsections. The first section is kinematics, the study of motion. We just finished it. The second section is statics, the study of forces on objects at rest. And the third section is dynamics, which is the study of forces on objects that are moving with respect to each other. In other words, the study of forces and the motion that they cause. Okay? And so we'll spend a set of videos on statics, and then by the next set of videos, we'll be ready to move to dynamics. Okay? So before we can do any of that, though, we need to talk about some definitions. And one of those definitions is forces. But before force, maybe inertia. I am sure you've all heard of the word inertia, if from nowhere else, then perhaps from Bill Nye, the science guy. And if you pause and think about it, what does inertia have to do with? And if I were to ask this in a classroom, lots of times I get, has to do with an object wanting to keep moving, or how hard it is to stop an object. In sports, sometimes a coach will say, use your inertia to bring, to help you do this. So really, inertia came about, our understanding of inertia came about probably the 2 people that were most influential were Galileo and Newton probably gets the most credit. But inertia is simply the natural tendency of an object to want to remain in its current state. In other words, if it's at rest, it wants to stay at rest. And if it's in motion, it wants to stay in motion. Now, you should understand the one, if it's at rest, it wants to stay at rest. This is why it's difficult to get out of bed in the morning. You have to overcome your inertia to get out of bed. Wants to stay in motion, it might be like if you're running down the hall, if you're running in a field and someone's in front of you, you know how hard it is to stop. Even though you want to stop, you have to overcome your inertia. So the object, in which case, this case would be your body, wants to stay in motion. Okay? Now, how much inertia an object has is directly dependent upon its mass. If you think about it, it's going to be a lot easier to stop a tiny object than it is a larger object. It's why you might pull out in front of a Toyota Corolla and think I might have time, and if not, he'll slow down. But you probably wouldn't do the same thing with a transport truck. And for the record, you shouldn't pull out in front of either of those unless you know you have enough time. But we know almost innately that it's going to take the transport truck, it's going to be harder for the transport truck to stop. And even though if they're going the same speed, and it's because of the mass. So inertia is directly linked to an object's mass. The more mass an object has, the more inertia it has, the more natural tendency it has to want to stay in the current state of motion. Now, this takes us back to the early scientists had this dispute, and because they thought if something was moving, then there must be a force acting on it. And this, of course, caused confusion. So imagine all of us who were in hockey withdrawal. Imagine a hockey puck sliding across the table. It's not going to stay in motion because there's friction that's going to slow it down. But if we took it to the rink and we slid it on the ice, it would slide a lot further before it stopped. And if we Zambodied the ice really, really well, we could even, and maybe we turned the puck into a hockey ball so that it's rolling, we can imagine that that ball is going to take a long time to slow down. So now the early scientists, when they would be looking at that, they would be thinking that there was some force making this object move. And it was Galileo who first suggested, no, that's an object's inertia that's keeping it moving. If I hit a hockey ball with a stick, then its inertia is going to keep it going, and it'll only stop if there's a force acting against its motion. Okay? That, of course, leads us to the question of what is a force? So there was a lot of debate about this. What is a force? Eventually, scientists came to agreement a force is simply a push or a pull on an object. Some people would want to say it's a push or a pull on an object that makes the object move. But that's not necessarily true. Imagine that I'm in my classroom and I'm pushing on the lab bench. I could be putting a huge force on that lab bench, but there's no way with my upper body muscle that I'm going to move that lab bench. But it's not because I'm not putting a force on it. So a force does not have to result in the object moving. Okay? Sometimes it might. It depends on how big the force is and how big the object is. Okay? So the simple definition of a force is a push or a pull on an object, and we could put here that may result in a change of the object's motion. That may result in a change of the object's motion. May. Okay? Not must.